Welcome. Today, we are going to talk about something so familiar that most of us never think about it. The ability to turn darkness into light with the flick of a switch. We do it dozens of times a day without a second thought. But there was a time, not so long ago, when darkness fell and the world simply stopped. When night meant danger, cold, and the end of productive activity for most people on Earth. The story of how that changed is the story of one of the greatest practical revolutions in human history.
It is strange to think about how recent it is. Electric light is less than 150 years old.
Less than 150 years. Your great-great-grandparents lived in a world without it. They went to bed when it got dark, or they sat by a candle or a gas lamp that gave off weak, flickering, sometimes dangerous light. The bright, reliable, controllable light that we take completely for granted was simply not available to them.
And one man more than anyone else is associated with changing that.
Thomas Edison. Though as we will see, the story is more complicated than the legend of a lone genius who invented the light bulb. It is a story about persistence, about teamwork, about business and competition, and about the enormous infrastructure that had to be built around a single invention to make it useful to the world. Let us begin in the dark, where the story starts.
What was life actually like before electric light? How did people manage?
For most of human history, the primary sources of artificial light were fire in its various forms, candles made from animal fat or beeswax, oil lamps burning plant or animal oils, torches, fireplaces. These sources of light were expensive, time-consuming to maintain, and gave off relatively little light compared to what we are used to today.
And they were also dangerous.
Extremely dangerous. Fire indoors has always been a serious hazard, and cities built largely of wood burned regularly and catastrophically throughout history. But by the 19th century, a new form of lighting had become widespread in cities, particularly in Europe and North America. Gas lighting. Coal gas was produced by heating coal in enclosed chambers, and this gas was piped through underground networks to street lamps, shops, theaters, and wealthier homes.
Gaslighting sounds more modern than candles. Was it a significant improvement?
It was a significant improvement in some ways, and a serious problem in others. Gas lamps gave off more light than candles, and were easier to manage once the gas network was in place. By the mid-19th century, gas-lit streets in major cities like London and Paris were genuinely impressive compared to the near-total darkness that had previously fallen at night. Theaters, restaurants, and shops could stay open longer. The social life of cities began to extend into the evening hours.
But the problems.
The problems were significant. Gas leaked. The pipes were imperfect. The connections were imperfect. And gas leaks in enclosed spaces could cause explosions or silent suffocation. The flames themselves were a constant fire hazard. The light was still relatively dim and flickering compared to what would eventually be possible with electricity, and the gas produced combustion products that were unpleasant and unhealthy in enclosed spaces.
So even with gaslighting, the situation was still far from ideal.
Far from it. And scientists and inventors had known for decades that electricity offered a potentially far superior alternative. The arc lamp, which produces light by passing an electrical current through a gap between two carbon rods and creating a continuous spark, had been demonstrated as early as the 1800s. Arc lamps were extraordinarily bright. They were used for lighthouses, for public squares, and for large indoor spaces like factories and theaters.
So arc lamps already existed. Why was the electric light bulb still needed?
Arc lamps had two fundamental problems that made them unsuitable for everyday domestic use. First, they were far too bright. The light of an arc lamp is like a piece of the sun. It is far too intense for a home or a small room. You cannot comfortably read by an arc lamp. Second, they required constant attention. The carbon rods burned away continuously and had to be adjusted manually to keep the gap at the right distance. You needed a dedicated operator to keep an arc lamp running.
So what was needed was a light source that was bright enough to be useful, but controlled enough to be comfortable, and that could run without constant attention.
A soft, steady, self-contained light that could be left running safely in a home or a shop. Something that behaved more like a candle in terms of its comfortable scale, but without the fire hazard and without the need for constant tending. This was the problem that inventors across Europe and America were racing to solve in the 1870s. And it was the problem that Thomas Edison decided to attack with his full attention and all the resources at his disposal.
What made Edison different from the other inventors working on the same problem?
Several things. Edison had already established himself as a successful inventor and a clever businessman. His invention of the phonograph in 1877 had made him world famous and had demonstrated that his laboratory in Menlo Park, New Jersey, was capable of producing genuinely revolutionary results. He had financial backers who trusted him and were willing to invest in his projects.
And he approached the problem differently from individual inventors working alone.
This is crucial. Edison did not work alone. He had built at Menlo Park what was essentially the world's first industrial research laboratory. He had a team of skilled experimenters, machinists, mathematicians, and specialists who worked together under his direction. He could pursue multiple approaches simultaneously, run many experiments in parallel, and bring diverse expertise to bear on a single problem. This was a new model for invention, and it was enormously more powerful than the individual genius working in isolation.
So Edison industrialized the process of invention itself.
That is exactly right. And he approached the electric light problem with characteristic boldness. He publicly announced in 1878 that he would solve the problem of the incandescent electric lamp within a few weeks. The newspapers celebrated him. Gas company stocks fell. And then the real work began, which turned out to be considerably more difficult than his public announcement had suggested.
So Edison had announced he would solve the problem in weeks. How long did it actually take?
More than a year of intensive work. And during that year, the Menlo Park Laboratory consumed an extraordinary amount of effort, money, and material in the pursuit of a solution. The core problem was the filament. The basic principle of an incandescent bulb is simple. Pass an electrical current through a thin material, and the resistance of the material causes it to heat up and glow. But finding a material that would glow brightly without immediately burning up or breaking was extraordinarily difficult.
Why was that so hard? There must be many materials that glow when heated.
Many materials glow when heated. The problem is that most of them also react with the oxygen in the air when they get hot enough to glow, and they burn up almost instantly. The solution to this problem was to put the glowing filament inside a glass bulb and remove the air, creating a vacuum. Without oxygen, the filament could not burn. But even in a vacuum, most materials that were tried either melted, vaporized, or became brittle and broke after very short periods of operation.
So they needed a material that could survive extremely high temperatures in a vacuum for a long time.
For a commercially useful period of time. A bulb that lasted an hour was useless. A bulb that lasted a day was interesting, but not practical. Edison aimed for a bulb that could last hundreds of hours, long enough to be a genuinely practical replacement for gas lighting. And finding the right material required testing an enormous number of candidates.
How many materials did they actually test?
The counts vary, and some may be exaggerated, but Edison and his team tested hundreds and possibly thousands of different materials as potential filaments. They tried various metals and metal alloys. They tried carbon in different forms. They tried natural fibers that had been carbonized by heating them in the absence of air. They tried hair, thread, cardboard, and various plant fibers.
That sounds like an almost random process of trying everything available.
It was more systematic than it sounds. Edison and his team had a theoretical understanding of what properties the ideal filament needed. It needed high electrical resistance, so that a short length of it would generate significant heat and light without requiring enormous amounts of current. It needed to be stable at high temperatures. It needed to be workable, meaning it could be formed into thin threads and shaped as needed. These criteria guided the search even when the search itself involved a great deal of trial and error.
Edison famously said something about failure during this period.
He said that he had not failed. He had found 10,000 ways that did not work. Whether he actually said exactly those words, or whether the quote has been simplified over time, the sentiment reflects something genuinely true about how he approached the work. Each failed material told him something about what properties the right material needed to have. Failure was not wasted effort. It was information.
That is a particular kind of mental discipline. Most people find repeated failure discouraging.
Most people do. And the team at Menlo Park was under real pressure. Edison had made public promises. His financial backers were watching. The newspapers were following the story. Every week that passed without a solution was a week of public scrutiny and private anxiety. Maintaining the discipline to keep working systematically under those conditions required extraordinary persistence.
And the solution, when it came, was almost surprising in its source.
In October 1879, Edison and his team were working with carbonized thread as a filament material. They had carbonized a piece of cotton sewing thread by heating it carefully to drive off everything except the carbon structure. This carbonized thread, placed inside a vacuum bulb, survived for more than 40 hours of continuous operation before failing. It was not perfect, and Edison knew immediately that the material could be improved. But it was long enough to demonstrate that an incandescent bulb was genuinely practical.
40 hours. That was the breakthrough.
That was the proof of concept. And Edison did not stop there. He and his team immediately began searching for better carbonized materials, and they found one that performed significantly better. Carbonized bamboo. Bamboo fiber, when carefully carbonized, produced a filament that could burn for over 1,000 hours. This became the basis for the first commercially produced Edison light bulbs.
Bamboo from where?
Edison sent collectors to search for the best varieties of bamboo around the world, from Japan, from China, from South America, from various parts of Asia. The search for the ideal bamboo variety involved the same systematic approach as the original filament search. Eventually, a Japanese bamboo was found that performed best, and it was used in Edison's commercial bulbs for several years, until better synthetic carbon filaments were developed.
The solution to an American technological problem ended up coming from a Japanese plant.
Innovation rarely respects national boundaries. The best material was the best material regardless of where it grew, and Edison was pragmatic enough to follow the evidence wherever it led, across the world if necessary. That pragmatism, combined with his willingness to keep working through failure after failure, is what ultimately produced the result that changed the world. So the carbonized thread filament survived for 40 hours in October 1879. What happened immediately after that breakthrough? Edison understood instantly that this was the moment he had been working toward. But he also understood that a working prototype in the laboratory was very different from a product ready to show the world. He and his team worked intensively through the following weeks, refining the bulb design, improving the vacuum pump to create a better vacuum inside the glass, and testing the bamboo filaments that were already showing promise as a superior alternative to the cotton thread. And then came the public demonstration. On New Year's Eve of 1879, Edison staged a public demonstration at Menlo Park that became one of the most celebrated events in the history of technology. He strung electric lights along the roads of the Menlo Park property and lit them all simultaneously. Trains brought visitors from New York and surrounding areas. Hundreds of people walked through the grounds of the laboratory in the winter night, surrounded by the soft, steady glow of electric lights, unlike anything they had seen before. What was the reaction of the people who saw it? By all accounts, it was one of wonder and disbelief. People were accustomed to the flickering, yellowish light of gas lamps or candles. The electric light was different in quality. It was steadier, cleaner, and could be turned on and off instantly without the need for matches or the smell of gas. Newspaper accounts from the following days described the scene in almost mystical terms. One reporter wrote that the light was soft, mellow, and grateful to the eye. That phrase, grateful to the eye, captures something important. The quality of light matters, not just the quantity. Edison understood this intuitively. He wanted his light to be pleasant to live with, not just technically functional. This is why he worked so hard on the specific characteristics of the filament and the bulb design, aiming for a warm, comfortable glow rather than the harsh brilliance of the arc lamp. The light had to feel right, not just work. Can you explain the science of why the bulb actually worked? Why did the vacuum matter so much? The key insight is that combustion requires oxygen. When a material gets hot enough to glow, it also gets hot enough to react rapidly with oxygen in the air, which is the process we call burning. If you remove the oxygen by creating a vacuum inside the glass bulb, the filament can reach the temperatures needed for incandescence without burning. The filament still slowly evaporates over time, which is why bulbs eventually fail. But the process is slow enough to allow hundreds or thousands of hours of operation, and the glass bulb itself served as the container for the vacuum. Yes, creating a good vacuum was actually one of the significant technical challenges of the project. The vacuum pumps available in the 1870s were not perfectly efficient, and trace amounts of remaining gas inside. The bulb could significantly shorten the filament's life. Edison's team worked hard on improving their vacuum technique throughout the development process, and better vacuums were one of the key factors in extending the life of their bulbs.
The light itself looked magical to people seeing it for the first time, but Edison was already thinking beyond the bulb.
Immediately, Edison was not thinking about selling light bulbs. He was thinking about selling light. And to sell light to homes and businesses across a city, he needed something that did not yet exist anywhere in the world. He needed a complete electrical power system, including generators to produce electricity, cables to carry it through the streets, and meters to measure how much each customer used so they could be charged for it.
So the light bulb was just the visible tip of an enormous invisible system that had to be built from scratch.
Edison himself said that the bulb was only a small part of the problem. The real work was creating the infrastructure. He compared it to the gas lighting system that already existed. When you lit a gas lamp, you were not just using a lamp. You were connected to a network of pipes, gasworks, distribution systems, and billing arrangements that had taken decades to build. Edison needed to build the equivalent of all of that for electricity, and he needed to build it fast enough that his financial backers did not lose patience and his competitors did not get there first.
Where did he decide to build the first electrical power system?
He chose Lower Manhattan in New York City. Specifically, he decided to build the first generating station on Pearl Street, in the heart of the financial district. This was a deliberate choice. By lighting the offices and buildings of New York's business district, Edison would demonstrate his system to exactly the people who had the money and the influence to adopt it widely. If the bankers and businessmen of Wall Street switched from gas to electric light, the rest of the world would follow.
That is a very strategic way of thinking about market adoption.
Edison was as much a businessman as an inventor. He understood that a technology is only as powerful as its ability to find customers. The Pearl Street station required 2 years of intensive work to build. Edison and his team had to design and manufacture generators large enough to power hundreds of bulbs simultaneously. They had to lay underground electrical cables through the streets of Manhattan. They had to design and install the meters and connection hardware in each customer's building.
And on September 4, 1882, the Pearl Street station went into operation.
At approximately 3 in the afternoon, Edison himself threw the switches at the Pearl Street station. Across a square mile of lower Manhattan, electric lights came on in offices, counting houses, and newspaper buildings. The New York Times, which was one of the first customers, reported the next morning that the light was soft, clear, and bright. It did not flicker. It did not smell. And when you wanted to turn it off, you simply turned a switch.
That simplicity must have been remarkable to people used to lighting and extinguishing gas flames.
The convenience was as revolutionary as the light itself. Gas lamps had to be lit with a match, adjusted for brightness, and extinguished carefully. Electric light responded instantly to a switch. It could be turned on and off dozens of times without any wear or inconvenience. This ease of use was not a trivial detail. It changed how people thought about light and how they incorporated it into their daily lives.
The Pearl Street station was a success, but Edison was using direct current, DC electricity. Why did that become a problem?
Direct current has a fundamental physical limitation. When you transmit electrical power over long distances, the voltage drops and significant energy is lost as heat in the wires. To compensate, you either need very thick and expensive copper cables, or you need to generate the electricity close to where it will be used. Edison's Pearl Street system served only about a square mile of Manhattan. To serve a larger area, you would need another generating station nearby, and then another, and then another.
So to power a whole city with direct current, you would need generating stations spread throughout the city.
Dozens or hundreds of them in a large city. This was expensive, complicated, and inefficient. Edison knew this was a limitation of his system, but he had invested so heavily in direct current infrastructure and held so many patents related to it that he was deeply reluctant to acknowledge the problem publicly or to consider switching to an alternative.
And the alternative was alternating current, AC.
Alternating current has a crucial advantage for long-distance transmission. Unlike direct current, which flows continuously in one direction, alternating current reverses direction many times per second. This property allows its voltage to be easily stepped up to very high levels using a device called a transformer, transmitted over long distances with minimal energy loss, and then stepped back down to safe levels for use in homes and businesses.
So with AC, you could have one large generating station serving a very large area.
A single large generating station could potentially serve an entire region. The economics were completely different from the DC approach, and the man who understood this most clearly, and who had the mathematical ability to design AC electrical systems, was a brilliant Serbian-American engineer named Nikola Tesla.
Tesla had actually worked for Edison briefly.
Tesla came to work at Edison's organization in 1884, and by most accounts he was recognized immediately as extraordinarily talented. But the relationship between the two men was difficult. Tesla believed strongly in the superiority of alternating current, and Edison was equally committed to direct current. The theoretical disagreements were compounded by personal and financial disputes, and Tesla left Edison's employ after less than a year.
And then Tesla found a more receptive partner in George Westinghouse.
George Westinghouse was a successful American industrialist and inventor who had already built a major business around his invention of the railway air brake. He understood large-scale engineering systems, and he had the resources to develop and deploy new technology. When Tesla approached him with his AC motor and generator designs, Westinghouse recognized their potential immediately and licensed Tesla's patents.
So the stage was set for a direct competition between two electrical systems.
A competition that became genuinely bitter, and that Edison pursued in ways that damaged his own reputation. As the advantages of AC power became increasingly apparent to engineers and investors, Edison responded not with technical arguments, but with a public relations campaign designed to frighten people about the dangers of high-voltage alternating current.
He tried to associate AC with danger.
He and his associates conducted public demonstrations in which animals were electrocuted, using alternating current, attempting to show that AC was inherently more dangerous than DC. They lobbied for the adoption of AC in the electric chair for executing condemned criminals, hoping to associate AC with death in the public mind. Edison even tried to have the word for death by electrocution be named after Westinghouse.
That is a surprisingly aggressive and personal campaign for someone with Edison's reputation.
It shows how much was at stake financially and reputationally for Edison. He had invested enormous resources in building a DC infrastructure. His patents and his business model were built around it. Acknowledging that AC was superior would mean acknowledging that his entire system needed to be replaced and that his competitors had been right. That was more than his pride and his business interests could easily accept.
And ultimately, AC won.
The decisive demonstration came at the 1893 World's Columbian Exposition in Chicago, where Westinghouse and Tesla won the contract to light the entire fair using AC power. The scale of the illumination was breathtaking. Hundreds of thousands of electric lights powered by AC generators lit the buildings, the grounds, and the waterways of the exposition. Millions of visitors saw electric light on a scale that had never been achieved before and saw that AC could deliver it safely and reliably.
After that, the outcome of the current war was essentially decided.
The Niagara Falls Power Project, completed in 1895, sealed it completely. AC generators at Niagara Falls transmitted electrical power to the city of Buffalo, 20 miles away, at voltages that would have been impossible with DC. The ability to generate power at one location and transmit it across long distances transformed the economics of electrical power entirely. Within a decade, AC power was the standard throughout the developed world, and it remains so today.
So the electricity we use in our homes right now is the system that Tesla and Westinghouse built, not the system Edison championed.
In terms of the fundamental AC architecture, yes, Edison lost the current war. But it is important to note that his contribution to the electrical age was still immense. He invented the complete system of incandescent lighting, built the first practical electrical power distribution network, and demonstrated to the world that electrical power could be a commercial reality. The current war was a battle within a revolution that Edison himself had started.
Once electrical power systems were established, how quickly did electric light spread to ordinary people's lives?
The spread was rapid by historical standards, but still took several decades to reach most of the population, even in wealthy countries. In 1882, when the Pearl Street Station opened, electric light was a luxury available only to a small number of businesses and wealthy individuals in a few city centers. By 1900, perhaps 10% of American homes had electricity. By 1930, that number had risen to about 70% in urban areas, though rural areas lagged far behind.
So there was a significant gap between the invention and the widespread adoption.
There always is with transformative technologies, building the infrastructure, manufacturing the equipment at scale, training the workers, establishing the regulations and safety standards, and making the whole system affordable enough for ordinary families. All take time and require enormous investment. The electrical industry grew steadily through the late 19th and early 20th centuries, driven by falling costs, expanding generating capacity, and the development of an ever wider range of electrical appliances that gave people reasons to want electricity beyond just lighting.
What was the immediate effect on people's daily lives when they did get electric light?
The most immediate and dramatic effect was on time. Before electric light, the organization of human activity was largely dictated by the sun. People woke at or after sunrise and wound down their activities as darkness fell. The workday, the school day, the shop day, all were shaped around the availability of natural light, with candles and gas lamps providing only a limited and expensive extension into the evening hours.
And electric light broke that constraint entirely.
It did. With reliable, affordable, bright electric light, there was no longer any physical reason why productive activity had to stop when the sun went down. Factories could run through the night. Shops could stay open into the evening. Students could read and study after dark without straining their eyes by candlelight. Offices could function on schedules that were not dictated by the seasons or the time of sunset.
That sounds liberating, but it also sounds like it could be demanding. Did the extension of the working day have negative consequences?
This is one of the more complex aspects of the electric light revolution. In the short term, the ability to work at night was often used to extend the working hours of factory laborers, many of whom had little power to resist the demands of their employers. Night shifts became possible in ways they had not been before, and the line between work time and rest time became more negotiable, often in ways that benefited employers more than workers.
So the same technology that freed people from darkness also created new pressures.
Technology rarely has purely positive or purely negative consequences. It changes what is possible, and then human societies, with all their conflicts and inequalities, determine how those new possibilities are used. Electric light made night work possible. Whether that possibility was used well or badly depended on the social and economic conditions of the time and place.
What about education? You mentioned students being able to read after dark.
The effect on education and literacy was significant, particularly for people who worked during the day and could only study in the evening hours. Before electric light, evening study was difficult and hard on the eyes. The improvement in lighting quality made sustained reading much more comfortable and practical. Libraries extended their hours. Evening schools and adult education programs became more viable. The general availability of light in the home encouraged reading as a leisure activity in ways that contributed to the spread of literacy.
So light democratized knowledge to some extent.
It helped do so as part of a broader set of changes in education and publishing that happened during the same period. Books were becoming cheaper, printing was improving, public libraries were expanding. Electric light was one of several factors that made books and reading more accessible to more people.
What about the transformation of cities? The night skyline of a modern city is one of the most distinctive images of the modern world.
The visual transformation of cities was extraordinary and happened relatively quickly once electrical systems were established. A city at night before electric light was a place of deep shadows, with small pools of gas lamplight at intervals along the major streets and near total darkness in side streets and residential areas. It was a place where you moved carefully, where crime flourished in the darkness, where social activity largely ceased.
And electric light changed all of that.
It changed the night city completely. bright shop windows displaying goods to evening pedestrians, electric signs advertising theaters and restaurants, well-lit streets where people felt safe to walk after dark. The development of a genuine evening economy with restaurants, theaters, music halls, and later cinemas, all depending on the ability to attract customers after sunset.
The entertainment industry, as we know it today, is in some sense a product of electric light.
Deeply so. The modern theater, the cinema, the concert hall, the sports stadium with its floodlights, the amusement park. All of these depend on the ability to create controlled lighting environments that attract and hold audiences after dark. The entertainment economy that employs millions of people and generates enormous cultural output would simply not exist without the electric light.
And looking at a modern city from above at night, you see something that would have been completely unimaginable to anyone living before 1879.
Completely unimaginable. The view of a major city from above at night. Millions of lights forming patterns that trace the streets, the buildings. The highways is one of the most dramatic visual demonstrations of how thoroughly human beings have transformed the surface of the planet. We have, in a very real sense, extended day indefinitely. The rhythm of light and dark that governed every human society for the entire history of our species has been fundamentally altered.
And that alteration has costs as well as benefits.
Yes, and this is something that scientists have become increasingly concerned about in recent decades. Artificial light at night disrupts the biological rhythms of many organisms, not just humans. Birds that navigate by stars become confused by artificial light and collide with buildings. Insects that are attracted to light are drawn away from the ecosystems that depend on them. Sea turtle hatchlings that should instinctively move toward the brightest horizon, which is the sea reflecting the night sky, instead move toward beachfront lights and die.
And for humans, there are health effects from too much artificial light at night.
Research has shown that exposure to artificial light at night, particularly the blue wavelengths emitted by modern LED screens and lights, suppresses the production of melatonin, a hormone that regulates sleep. Disrupted sleep patterns are associated with a wide range of health problems, including increased risk of certain cancers, cardiovascular disease, and metabolic disorders. The same light that liberated us from darkness may, when used without care, create its own health burdens.
So the story of electric light is not simply a story of human triumph. It is also a story about the need to manage a powerful technology wisely.
That theme runs through so many of the stories we tell about human innovation. Fire gave us warmth and cooking and civilization, and also the capacity for enormous destruction. The printing press spread knowledge and also propaganda. The discovery of nuclear energy offered both clean power and weapons of mass destruction. Electric light ended the tyranny of darkness and also created light pollution, ecological disruption, and sleep disorders. Every powerful tool requires wisdom in its use.
Edison could not have imagined all of this when he stood in the Menlo Park laboratory holding a glass bulb with a glowing filament inside.
He was thinking about replacing gas lamps. He was thinking about the business model, about the patents, about the competition, about making the system work reliably, enough to convince people to pay for it. The long-term ecological and health consequences of illuminating the entire surface of the Earth were not something anyone was thinking about in 1879. They could not have been. The understanding of those consequences required a century of science and observation that had not yet happened.
That is something humbling about technological progress. You solve the problem in front of you, and you create problems you cannot yet see.
And then the next generation inherits both the benefits and the new problems, and has to develop the wisdom to manage both. This is not a reason to stop innovating. It is a reason to think carefully, to monitor consequences, to remain open to adjusting course when new understanding demands it.
Looking back at the whole story, from the gaslit streets of the 1870s to the satellite images of Earth, glowing at night that we can see today, what strikes you most?
What strikes me most is the combination of individual vision and collective effort. Edison had the vision, the determination, and the organizational genius to make the incandescent bulb a practical reality. But turning that single invention into the global electrical infrastructure we depend on today required thousands of engineers, investors, workers, regulators, and scientists working over generations. No single person created the electric age. One person lit the first spark, and many others kept it burning.
And the competition between Edison and Tesla and Westinghouse, which was so bitter at the time, ultimately produced a better outcome than any single approach would have.
The current war was painful and involved real dishonesty on Edison's part. But the competition between DC and AC systems drove rapid development, forced both sides to improve their technology, and ultimately produced a global electrical standard that has served humanity well for well over a century. Competition, even when it is fierce and sometimes unfair, can be a powerful engine of progress.
The light bulb itself has changed since Edison's time. We no longer use incandescent bulbs in the way he designed them.
The technology has evolved continuously. Tungsten filaments replaced carbon, lasting much longer and burning more brightly. Fluorescent lighting offered much greater efficiency, and today, LED lighting is rapidly replacing all earlier technologies, using a tiny fraction of the energy that Edison's original bulbs required to produce the same amount of light. The principle Edison demonstrated, using electricity to produce controlled, reliable, pleasant light, remains. But the implementation has been refined almost beyond recognition.
So Edison's invention is still with us, but transformed.
That is how technology works at its best. The fundamental insight endures and continues to be developed, while the specific implementation improves with each generation. Edison gave us the concept of the electrical light. Every engineer and scientist who worked on improving it since then has contributed to where we are today.
And where we go from here? Managing light pollution, developing smarter lighting systems that work with our biology rather than against it, extending the benefits of electric light to the parts of the world that still lack reliable electricity.
About 750 million people on Earth today still do not have reliable access to electricity. For them, the revolution that Edison started is still incomplete. The extension of electrical light to every human being on the planet remains one of the most important and achievable goals in global development. The technology exists. The challenge is economic and political, not scientific.
So the story that began in a New Jersey laboratory in 1879 is still unfinished.
The best stories always are. Edison threw a switch, and the lights came on in Lower Manhattan. The work of making sure those lights reach everyone and of using them wisely when they do continues. Thank you for joining us today on this journey from darkness to light.
From a single glowing filament to a planet that never sleeps. What a journey it has been.
And what a journey it still has ahead.